So for this first limit here, positive infinity, let's see what it looks like if we were to plug in positive infinity. So with infinity plugged in everywhere into the domain of the function, infinity squared's infinity subtracted by 2 times infinity minus 1. This is always bigger than this, and subtracted by 1 still won't bring it into the negatives. This is guaranteed to be positive. This is guaranteed to be positive, and as we approach infinity, going in the right direction, it keeps getting bigger and bigger. All those numbers inside there. This parentheses always gets bigger because this outpaces this because it's being squared. This always gets bigger, so the limit is infinity. But if we were to plug in negative infinity, you can't really tell, those are negative signs there though. First note that this is a positive number. Okay, raising a number to a negative power doesn't change its sign; it just makes it really, really small. So this number is approaching 0, because as you go off to infinity, raising a number to a bigger and bigger, a larger negative number in here, like negative a billion, negative a trillion, that makes this become a bigger and bigger denominator in the fraction. So this is going to approach 0. And then checking inside here, a negative infinity being squared, this will be a positive number, subtracted by 2 times negative infinity. So this is plus 2 times infinity. This is all going to be a positive. This is going to be some constant, but it's going to be multiplied by 0. Because inside here is outpaced by the power happening outside here. Infinity to the second power is always outpaced by e to the infinity power. A power always outpaces a constant power. A variable power always outpaces a constant power. So let me say that again. That was wordy. A variable power, when it's going off to infinity, always outpaces a power that's a constant going off to infinity. So this will not be as big as this. This 0 will happen before this goes off to infinity. So we would say that this equals 0. For part B, define where a function is increasing. A function only changes from increasing to decreasing and vice versa if it's continuous, where the first derivative equals 0. So let's take the first derivative of this function. You can identify 2 distinct functions of x here, the red and the blue. And if we recall, the product rule says that we have 2 functions of x being multiplied to each other. It's the derivative of f times g kept the same plus the derivative of g times f kept the same. Kind of ran out of room there, but using that product rule, the derivative of this first function, this first red one, is in parentheses 2x minus 2, because we have to multiply all of what that derivative is to the second function kept the same. And then product rule says you need to add to that the derivative of the second function with the first function kept the same. Derivative of e to the x is itself, e to the x. It's its own rate of change. So here is the derivative of the original function. To find out where it's either increasing or decreasing, we need to find the critical points. So we're going to set the derivative equal to 0. We're going to find out where those slopes equal 0. So we've taken the derivative, we set it equal to 0, so let's go find those critical points. The trick to solving this equation is to notice in blue that you have e to the x common in both terms. Factor out that e to the x, and what's left over goes in parentheses. 2x minus 2 plus x squared minus 2x minus 1. And really forget about the parentheses because you have a plus in between them. So when you add up all those terms, you have x squared, and then you have a 2x plus a negative 2x, that perfectly cancels out. You have a negative 2 plus a negative 1, so you got a negative 3. Okay, so we've taken the derivative, we factored out an e to the x, which gave us this, and then we simplified. So now it should be fairly clear what the zeros are, because this term is a number raised to an exponent power that can never be 0. It can get infinitely close with huge negative numbers. It can never be 0. But here it can be 0 if x is the square root of 3 or if x is the negative square root of 3. Those are the zeros. So since the question asked where the function is increasing, we know these are the critical points, and we say a function is increasing if its slopes are greater than 0. So we got to find out where our second derivative, which is this guy up here, where the second derivative is greater than 0. At these points, the second derivative equals 0, the slope is 0. And if you plug in x equals 0 into your second derivative, which is a point in between these two values, if you plug x equals 0, then the second derivative is negative 3. So that means it's I kind of lost my apostrophe. There we go. If we tested a point in between our two zeros, and we found that the rate of change was negative 3. So that means it's decreasing in between these two guys. So we have to test to the left of negative square root of 3, to the right of negative square root of 3, and see if those are increasing. If you plug in a value of negative 2 into the derivative, you get this, which is a positive number because it's 1e to the negative second when you simplify that. So that means it's increasing for values to the left of the negative square root of 3. Likewise, we can plug in a number to the right of our zeros to check to make sure that that one's increasing too. You get these two values for the terms, so when you simplify you get e to the second. This is also a positive number, so it's increasing to the right of these points. So it's a from negative infinity to negative square root of 3, and that's actually the letter U, union square root of 3 to infinity. These are the intervals for which it is increasing. So for part C of this problem, we need to find the intervals in which the graph of f is concave down. So that means we need to find the second derivative because it is concave down where the second derivative is less than 0. The rate of change of the slopes is less than 0. So this at the bottom of the screen was our first derivative. The second derivative is going to be calculated in much the same way. We've got to use the product rule. Okay, because this in red is one function, this in blue is another function. So for the first term, the derivative is going to be 2 times e to the x plus 2x minus 2 e to the x. The derivative of the first term times the second term kept the same, plus the derivative of the second term, which is just e to the x, times the first function kept the same. So there's the first term. Now we need to repeat the same process for this term down here to find the second derivative. And that's going to be, derivative of the first term is 2x minus 2 e to the x plus x squared minus 2x minus 1. Derivative of the second term kept the same. So there's our second derivative. We need to find the zeros for this. We need to find an inflection point so we can evaluate where it's less than 0, where it's greater than 0. But before we try to do any crunching to find out where it's negative and where it's positive, check this out. You get 2x minus 2 e to the x, 2x minus 2 e to the x. Those are the same thing. We can combine those terms. And actually all these have an e to the x. So let's factor out an e to the x from all these. And what's left over is going to be this stuff when you factor out an e to the x. 2 plus 2x minus 2. Notice I'm dropping the parentheses because we're adding. So plus in front of a parentheses doesn't affect it. X squared minus 2x minus 1. There, and we've got some like terms we can combine there. When you combine like terms, you should get this in the parentheses here, and that can be factored. How about x plus 3? How about, I don't know what I'm doing with colors anymore, but how about x minus 1? Because now these two multiply to be negative 3, they add up to be negative 2. So it's factored, and when it's factored, it's clear to see what the zeros are. X equals negative 3, x equals 1 are the zeros. So we found out that negative 3 and 1 are the zeros. So we want to find where it's concave down. So we want to find out where it's negative. And it could be negative on this side, negative here, or negative here. We've got to test them all out. And if you check x equals 0, well, properly we should write like that because we're plugging in 0 into the second derivative. If you plug 0 in here, you get 3. 0 in here, you get negative 1. 3 times negative 1 gives you negative 3. And e to the 0 is 1. So you got negative 3 for this value. So there we go. It's concave down. We know at least between negative 3 and 1 because these are the potential inflection points. We tested a value by plugging in 0 in, and it was less than 0. So it is concave down. You gotta check these ones out. How about negative 4? And how about 2? Plug those guys into this original second derivative, and you'll find out that these are both positive numbers. The only place where the second derivative is less than 0 is between these two numbers. So we'd say concave down for negative 3 less than x less than 1. Or, you could put that in interval notation. And you just showed it's concave down by taking the second derivative and plug in numbers between the inflection points.